The previous 2 videos in the series have focused on introducing many concepts in quantum physics. If you haven't already, I strongly recommend watching those 2 videos first to get a better grasp on what exactly quantum physics is. The playlist to all the videos in this series is in the card in the top right. Using this knowledge in the past videos, we will introduce one last concept known as superposition and finally dive into quantum computing and see why these quantum computers are regarded to be the future of technology. If you watched the first video in the series, you might remember our discussion of waves and how they can add to each other in some places and destroy each other in others. We also called this addition of waves superposition. However, in terms of quantum physics, this addition of waves isn't the only concept referred to as superposition. Rather, any addition of 2 states is known as superposition. To understand this concept better, recall that at the small quantum level, it is impossible to tell exactly how the particles are acting. On a normal scale, if a coin was flipped, it would either land on heads or tails, and it is clear that only one of these combinations would be true at a given time. However, if a so-called quantum coin was flipped, the result can't be so easily determined. Thus, until more complex tools are used to carefully observe the results of the coin flip, this quantum coin exists in a state of being both heads and tails. We say that it is in a superposition of these 2 states. Only once the complex tools are used to observe the side the coin flipped on, the coin will be in one of these 2 states, and we say that the superposition collapses into being either heads or tails. Assuming it's a fair quantum coin, there's a 50% chance that it would be heads, and a 50% chance that it would be tails with a random probability. Note the similarity between this superposition collapsing and the photons in the double slit experiment, where once we observed one of the photons going through a slit, then the photons stopped acting as waves and rather as particles. This is because the photons were in a superposition of going through both slits at once, and this superposition of the waves was interfering with each other. However, the superposition collapsed when we observed the photons, meaning that they only went through one of the slits and acted as particles. The double slit experiment is proof that superposition is not some abstract idea. It is a very real phenomenon for things on the quantum scale. In fact, the double slit experiment also serves to demonstrate another concept called interference. Recall that we said that waves could build up each other, called constructive interference, and destroy each other, called destructive interference. In general, when superpositions interact, they can affect each other and make certain specific results occur. In the double slit experiment, without interference of the superpositions, there wouldn't be the bright or dark spots on the screen since the waves don't cancel each other out or add to each other anywhere. It is only because the waves interfere with each other that this, interference pattern is created. Interference can take many forms. For instance, 2 quantum coins tossed at the same time might interfere with each other so that individually they are in a superposition of landing on heads or tails, but when they interact, it always occurs that one is heads and the other is tails. This specific example is called quantum entanglement and will be explored in the next video. Other examples of interference could be that the coins are more likely to each land on heads because of the interaction, or that there is no chance of them landing on heads if they interact. In general, whenever 2 superpositions interact, it will create a new superposition of both things with more outcomes. For instance, in the 2 coins example, there is always a certain probability of both being heads, a certain probability of one head and one tails, a certain probability of the other one being heads and the other being tails, and a certain probability of them both being tails. And note that these probabilities could be as extreme as 0 or 100, or it could be an even split of 25, 25, 25, and so on. It could be any combination of probabilities as long as they add up to 100%. And these new probabilities depend on the nature of the interaction and the original superpositions. However, it is important to note that the superpositions are not permanent, they always collapse once they're observed. And so at the end of the day, there is still only one final result. The difference the superposition makes is that before it is measured, interference can occur because of the uncertain nature of the states and create unexpected results. Okay, so at the quantum scale, objects can exist in superpositions of multiple states at once, and these superpositions can interfere with each other to change the probabilities of certain outcomes. But what does this have to do with computers? First, I must explain how a normal computer works. Everything that you see on your computer, from video games to this video that you're watching right now, is built up from a series of ones and zeros within your computer. These zeros and ones are made up from bits of data inside your computer, and each bit is always set to either a 0 or a 1. This means that as another bit is added to a computer, there is one more 0 or 1 which would be used in the computer's functions and data processing, which increases its functionality. However, in a quantum computer, these normal bits of data are not used, but rather qubits, which exist as not only 0 or 1, but it could be a superposition of 0 and 1. They could still just be 0 or 1, because the 0 has 100% or the 1 has 100%, but they could also exist as a superposition of half 0 and half 1, or 80% 0 and 20% 1, and so on. However, once the value of the qubit is measured, the superposition will collapse just like the coin earlier, meaning the final value of the qubit is either a 0 or 1 as earlier. It is only during the computational processes, when the qubits are moving around without being measured, that this superposition comes into play. Essentially, all these different combinations of superpositions could come together to create even more and more possibilities. In a normal computer, adding one more bit just adds one more bit of data, but in a quantum computer, it doubles the amount of possible superpositions, since the new qubit takes all the previous possibilities and adds one case where the qubit is 0 and another case where the new qubit is 1. And thus the processing power of the quantum computers grows exponentially because it doubles with every new qubit, while normal computers grow at a linear rate because it only adds one more with each bit. However, once the result is measured on a quantum computer, there is always only one output given because the superposition collapses, meaning while during the computations these quantum phenomena can be utilized to achieve higher processing speeds, when the final result is measured, it is identical to that of a normal computer. This allows for tasks which would ordinarily take millions of years on a normal computer to be completed in matters of minutes on a quantum computer, which is a very significant achievement. However, the usage of quantum computers are very specific to certain problems, meaning it's not that everybody would be given a quantum computer, as this wouldn't even be practical due to many errors which will be discussed in the next video. It is simply for very specific scientific advancements with data processing or quantum simulations or molecules in the body and more that quantum computers will truly be a game changer. However, these computers are not perfect, and in the next video in the series, we will look at some problems with quantum computers as well as one last quantum phenomenon used, called quantum entanglement. Now, throughout this video, I referred to the probabilities of certain outcomes to represent superpositions. For instance, something was 80% 0 and 20% 1. However, in order to actually do the math with qubits and superpositions in general, they must be represented as seen here, where alpha and beta are complex numbers, and 0 and 1 are the two possible states for each qubit. The probability of measuring a 0 or 1 from each individual qubit can still be found, but it is instead equal to the square of the absolute value of its respective complex coefficient. And note that in the bottom, where the two qubits are represented, the combination of the above qubits, 0, 0 means both qubits are 0, 0, 1 means the first qubit is 0 and the second qubit is 1, and so on. For instance, note how interference can occur if beta 1 is equal to 0, meaning that there is no possibility of the second qubit being a 1, and this is represented in the equation at the bottom, where all the possibilities with the second qubit being equal to 1 drop out to 0.